Hello guys, thank you so much for being with me in another machine learning tutorial video. In the previous video we talked about the application of gradient descent algorithm in regression problems. We said that sequential implementation is incorrect and correct implementation is simultaneous implementation. In the correct implementation we first calculated the gradients and then update the parameters. In the previous video, we also checked the gradient descent algorithm intuitively. At the end of the previous video, we talked about convex functions. A convex function is a function that if we connect 2 points above the image of these functions, these line segment will definitely be located above this function. We said that one of the features of this type of functions that we are interested in is that these functions have only one global optimal point. There are several types of gradient descent. What we have reviewed so far is also called the gradient descent of the vanilla version or the raw version. The characteristic of this type of gradient descent is that the differential is calculated in terms of all parameters and updates are applied to all data. If our data is very large, this method is not optimal. There is another method in which in each iteration, instead of applying the update to all the data, we perform this update only on a randomly selected data. This type of gradient descent is called stochastic gradient descent. There is also an intermediate method in which in each iteration the parameters are updated on a small random subset. This type of gradient descent is called the gradient descent with small group or mini batch gradient descent. In practice, the best type of gradient descent is this type, and it is relatively accurate. From now on, wherever we talk about a gradient descent, the default is this type of mini batch gradient descent. If we mean other types of gradient descent, we use their names explicitly. We say that we want a full batch gradient descent, or for example, we want a random gradient descent. By setting the right size for these batches, we can operate optimally. Research has shown that the size of these batches should not be too large. We have reviewed an example of house price estimation based on the size of the house only. In the real world, more parameters should be considered to estimate the price of houses. Such a problem is called multivariate linear regression. For example, we can consider the number of bedrooms, the number of floors, and the age of the house. In general, m features can be considered. Here we consider 4 features. As before, first we must have a training set and we must have a type of hypothesis of function. The number of features increased to 4, so the number of parameters is 5. The number of parameters is always n plus 1 if the number of features is n. Let's review the symbols again. We denote the number of training samples, which is the same as the number of rows in the training set table with m. We denote the number of features with n. We express actually the inputs with x's. For example, the second input is a 4-way vector, 4-dimension vector. We said that whenever we talk about a vector in this lesson, we mean column vector. I is the input count index and j is the feature count index. So there is no difference except that the function of the hypothesis has become more general. You can see that if we look at this hypothetical function, there is an asymmetry. For simplicity, we add an attribute x0 to the set, which always has a value of 1. It must make our task mathematically simpler. Okay, here we add x0 is equal to 1 as a factor multiplied in this theta 0 in order to have a symmetric formula here for the h theta x. The product of two vectors that are the same size is equal to the product of the one-to-one multiplication of peer-to-peer elements. So we can simplify the hypothetical function in this way. For this, we must use the concept of internal multiplication or dot multiplication of vectors. You must be familiar with these concepts from the course of linear algebra. Now we have to minimize the cost function again to reach the best parameters and finally the best hypothesis function. We use the same cost function as before, that is the function of sum of squares error. Only this time the function depends on more parameters. Everything is the same as before. Again, we need to update the parameters until the algorithm converges. Don't get too caught up in the math right now. You don't need these concepts to implement, but I prefer to mention these so that you can enter the world of machine learning with a better understanding. One of the main steps that must be done in the preprocessing phase is scaling. The second thing we want to talk about is the learning rate. The purpose of scaling is to ensure that the values of different variables and attributes fall within the same range. This makes the convergence speed of the algorithm much higher. For example, suppose we have two features. One is the size of the houses and the other is the number of bedrooms. You can see that the ranges of these values are very different. This causes problems. When we draw the shape of the cost function, instead of being circular, it looks like a ball that is stretched too far in one direction. Why is it too wide in one direction and too narrow in the other? Suppose theta 0 is 0. We have nothing to do with it. In the value of the hypothesis function, the variable x1 plays a greater role. To compensate for this difference, the value of theta 2 must be increased so that these two effects are equal. To moderate the effect of two sentences, something like this should happen. So the cost function looks like this. You can see it. Now we implement the gradient descent algorithm. We start from a random point. We move against the direction of the gradient, and now because the function is very narrow in one direction, we overshoot even if the alpha is not very large. So to prevent this zigzag movement, we scale the value of these features so that they are roughly in an equal range. Now if we draw the shape of the hypothesis function after scaling the features, you will see that it will be circular. This task actually is called preprocessing. Other tasks are also done in this phase, but one of the main tasks in the preprocessing phase is scaling. Now, if we want to implement the gradient descent algorithm again, we will go through a relatively smooth and fast path. For example, our algorithm has become 30 times faster. There are different ways to scale. It doesn't matter which method we use. For example, you can subtract the mean value from the characteristic value of each sample and divide the result by the dispersion. The same can be done for each feature in this order. The dispersion of the values of the features becomes almost equal. This method is one of the most common. You can also add a value equal to a half 0.25 to the sides of the image. This task is called standardization. In this order, the value of all features is between 0 and 1. This method is called mean normalization, which or average normalization, which you can see in the slides. It is very unlikely that there is a real-world problem that does not require scaling like this, but the next point is about determining the learning rate. We said that in gradient descent algorithm, one step should be moved against the gradient direction. We have to find the value of this step by experiment. We draw a graph after solving each machine learning problem. It should be the final shape of something. That is, from a certain point onward, this slope must become 0, which is the same meaning as the convergence of the algorithm. And because when this happens, the value of the cost function no longer changes. If we reach this chart, we can be sure that we have done the right thing. In the previous videos, we also said that if the value of alpha becomes too large, we will face the divergence of the algorithm. Whenever you see a stack of charts, you can be sure that your alpha is too large. Plotting the shape of the cost function can be very effective for judging the hyperparameter alpha. The main problem in solving machine learning problems is that setting these hyperparameters is not an easy task. So we need to choose a suitable value for alpha. A good way to choose the value of this hyperparameter is to first choose a very small value. You will probably encounter slow convergence of the algorithm. In this case, we understand that we need to make alpha a little bigger, a little larger. But how much? One way is to increase the alpha by 0.001 each time. But in some cases, if we want to add exactly the same amount of alpha, we have to run the algorithm millions of times. To avoid this problem, we multiply alpha by a number every time. For example, we multiply alpha by, for example, 3. Now we do the calculations again and draw the chart and the figure of the cost function. When we see that convergence is still slow, we increase alpha again. We repeat this until we reach an ideal figure. So the important thing in changing the alpha value is to use a logarithmic scale. It means to multiply alpha by a number or divide by a number. Do not use addition or subtraction. Now we want to free the hypothesis functions from the limitation to errors. It means that the hypothesis function can include polynomials of any degree. In what cases is the use of functions of a higher degree used? For example, two features are effective in estimating the price of a house. One is the width of the house. Here, for example, one is the length of the house. But we know that actually the length and width of the house is not very important. What is very important is the area of the house, which is equal to the product of the length and width of the house. So the new feature x can be defined as the production of x1 and x2. x1 and x2 are the length and the width of the house, and x is the area of the house. That is, in some cases, a feature itself is not very important, but for example, the product of two features, the ratio of two features to each other, and somehow the effect of two features on each other are important. In these cases, it is better to use second degree functions. In polynomial regressions, we are not limited to degree 2 and can use higher degrees as well. Maybe by increasing the degree of polynomial, the error and cost will be reduced. Now, for example, in this particular example, the hypothesis function of degree 2 and 3 is better than degree 1, but in this example, between degree 2 and degree 3, the function of degree 3 is better. Why? Because in the second degree function, if we continue the swing, we will face a parabolic function, and from one point on, when the size of the house increases, the price of the house decreases. We know that this is not the case, so here between these two, the third degree function is better, but it is strictly upward, and we are sure that it will not decrease from anywhere. But is this function necessarily the best hypothesis function? Obviously not. The only strictly ascending function is not a polynomial function of degree 3, but here it is superior to the second degree function. In this example, the function of degree half, which is the radical, is better called is better. This task is called feature engineering. This task determines that what features to consider: the size itself, root size, square. This is not an easy task. It cannot be taught, and it will only be possible under the shadow of experience. Our goal is for the algorithm to determine by itself which of these features it should consider. This is the goal that will be accessible through deep learning. So we investigated the gradient descent and its application in solving regression problems with the help of computer. Is this the only way to solve math problems? Obviously not, because regression problems were solved before the invention of computers. The second solution idea is a mathematical idea. Suppose we have this equation and we seek to find its minimum. We know from mathematics that to find this minimum point, we must set the differential equal to 0. That's the idea. However, here we want to discuss multivariable equations. Okay, I will continue the concepts in the next videos. I again highly recommend you not to miss upcoming lectures, because very practical and important tips are awaiting for you during the next videos. Have a nice time.